Hello, welcome to session number 31 in the series Analog Circuit Design. My name is Anurag Nigam, and this has been a long break, uh, after which I'm resuming these series again. Okay, so uh, this is what I'm presenting here is a 100 gigahertz PLL uh, for 6G applications. So basically, it goes from anywhere from 98 gigahertz to 108 gigahertz, right? And this is done in 7 nanometer CMOS process. So now one thing unique is that this is being done in ADS. And as far as the PDK is concerned, this is basically BSIM CMG models, right? Which are fitted by me uh, for your NMOS and PMOS devices, right? And they are scalable models which I have fitted, and they have process queue also modeled into it. So the way I did this modeling was, initially I did a simulation in COMSOL, a physics-based simulator, and I simulated uh, your fins, right, for different sizes, right? So this is a CMG tri-gate model, right? So I did the simulations, and then I extracted the parameters, and then based on that I did the modeling of 7 nanometer MOSFETs or FinFETs, right? And the fin width is 5 nanometer. So that I have earlier also shown on my LinkedIn account what I did. So anyway, so what I have is a 7 nanometer process here, PMOS and MOS. So what I'm showing here is a simulation which was run for almost 10 nanosecond to show the locking of the PLL, right? So basically this is going to lock, and this natural frequency is roughly 500 kilohertz. So basically, uh, let me show you what is the loop dynamics. Okay, so here in this project, let's look at the loop filter design. So I automated that. So I have written a bunch of equations for pole placements, and then I'm choosing a loop gain and for a loop bandwidth and for a given phase margin, and then the extent of frequencies, and based on that I calculate KVCO, and then I find out the total loop gain, right? K phi into KVCO by n, right? So based on that, this loop dynamics has been written, and the way it works is I can run a tuning, and here there are different options, right? So here this is a pole 3 placement with respect to pole 1. So basically I'm choosing a certain ratio, right, for pole 3 versus 1 ratio placement. And then I'm choosing a reference frequency here as 70 megahertz, and loop bandwidth as 1 megahertz, phase margin of 55, right? And KVCO is 4500, and gamma is the optimization factor, right, which is can range anywhere from 0.9 to 1.4. And accordingly I'm calculating these loop filter components C1, C2, C3, R2 and R3, and they translate into the circuit over here. So loop filter is going to be off chip. So this is the loop filter, right? So this loop filter is for a certain damping ratio, right? So if you see here, for settling time, for a given settling time and damping, so you can see over here, right? So you can see here that there will be a this settling time, and then there will be a natural frequency, and there will be a damping of this natural frequency, and that basically is over here. Right now the damping is actually this is redone anyways, so damping is around 0.9, right? And then your natural frequency is around 539k, right? So which translates to, like, each cycle being 2 microseconds or something like that. So basically I have to simulate this for sufficient time for this cycle to die down to a constant. So again, the simulation is going to be very lengthy, because you might have to simulate for like 20 microseconds for having this to settle. But then you will have to time step it as per 100 gigahertz bandwidth. So if you are doing a transient simulation for a PLL to simulate the locking, you will have to simulate for that time, and actually you have to simulate as per the sigma delta, right? So for example, there is a 16-bit sigma delta here for the fine feed. So 16 base means 2 raised to 16, and if you take 70 megahertz, so 70 megahertz 1 over 70 megahertz into 2 raised to 16, 65536, that will be around 1.3 milliseconds. So to have an exact ratio, if it exact fraction, you might have to simulate for 1.3 milliseconds. So the exact ratio will be given by the sigma delta. So that simulation time I could not run it because it's a very long simulation. So I have just simulation for 10 microseconds, and what I'm showing is that this is going to settle around 0.81 volts. And the way to compute, you can do FFT on this to compute the frequency, but I'm going to choose the final time period and then do an invert of that. So that is close to 105. So I'm basically designing, well, I'm putting in the values for coarse and fine feed to have 105 gigahertz as the output. So I'm close to 105 gigahertz in 10 microseconds, right? So it's very close here, right? It's off a few megahertz off because I haven't simulated for a long enough time. And second thing is, if you same time look at the ref frequency, that ref frequency would come close to 70, right? Your crystal frequency, right? 70 megahertz. So that's what you're going to go to, 70 megahertz. So your ref is 70 and your divided frequency should come to 70. That means that the loop is locked, and the output is that time will be the 70 multiplied by whatever the divide ratio is, right? So the divide ratio basically will come out to 105 gigahertz divided by that number. So let me explain you what this is. Okay, so let's go into this. Okay, so let me just exit the tuning mode. So what I showed you is a loop filter, right? And I showed you some settling characteristics here for a short duration of 10 microseconds. And my input target was 105. So I'll show you how I calculated 105. So basically, let's go to calculator. Okay, so let's say we are going to do 105, right? So go to standard. Okay, so 105 megahertz, right? So 105, so these many megahertz. So what I'm doing is, this is the VCO which generates 98 to 108, right? So this is that, I'll show you separately. So this is the VCO which I initially presented. It goes from 98 to 108, right? And the phase noise characteristics, everything I've shared in an earlier post, but I'm going to show you again. So this VCO gives out that kind of output, and that is divided by two fast dividers here. Okay, so because this is a 7 nanometer, right? So I'm able to divide this, run this divider at almost 100 gigahertz, right? So or beyond even that. So these two dividers are dividing by 4, right? So these are fast dividers. So 100 gigahertz goes down to 50, it goes down to 25. So that kind of range is there. The 105 will be divided by that. So let's go to the calculator. Okay, so this is divided first by 4. Okay, so I'm having a frequency of 26 gigahertz, 250 26 to 50 megahertz, right? So basically that goes into this multimodulus frequency divider, right? And that has a divide ratio, right? So basically let's divide by 70 to see what that divide ratio comes to be. So let's go to the calculator, and this is being divided by 70 gigahertz, 70 megahertz, sorry. So this leaves a divide ratio of 375. And then a sigma delta is producing an average of 3 to 4, right? So in this case, I will do a minus, because there is no fraction. That means sigma delta is given all 0 inputs, right? So 105 means that there is no fractional input. So this fine feed is all 0. But this fine feed all 0 doesn't mean that that is not going to do noise shaping. It's still going to do the noise shaping, right? And the average is going to be 3. So basically I'll minus from this 3. So then I am left with 372. So my coarse feed will be 372 and my fine feed is all 0. So 372 is what I have to feed. So let's look into programming calculator. What is 372? 372. So this decimal 372 translates to 10111100, right? So let's see what that is. So you start with 0 here. Okay, it's a 8-bit. So consider 8 bits here. Let me see, decimal. Okay, another thing I forgot. Okay, so 372 is not what is acceptable in 37 in your 8 bits. Now, how this works is the divide. If it is an 8-bit multimodulus divider, then the minimum divide ratio is 256. So basically, you can take 256 off of that. Okay, so take 256 off of that. So you are left with 116. Now 116 would be 0111, right? So that's 0 1 1 1 0 1 0 0, right? So this is 0 1 1 1 0 1 0 0. So basically you are feeding in 116. So 116 plus 256 is the minimum divide ratio of the multimodulus divider. It's 8-bit, right? So that will generate a divide ratio of 372, and then the 3 comes from the mesh 111 sigma delta modulator. So that is being added by this 8-bit adder, right? So this 3-bit output from the sigma delta is added to the 8-bit coarse input, which is 116, which is basically 0 1 1 1 0 1 0 0. So that's what you see here. Okay, now besides this, okay, there is a dithering circuit here, which basically feeds in the LSB. So the last 0 is basically fed in here, and this I'll show you the details of implementation. This is nothing but a ring oscillator with a frequency which is an irrational fraction of the 70 megahertz. So that's going to slide against 70 megahertz, generating a kind of a random response, right? So this the LSB bit, which is P0, is dithered by this dithering circuit, and this dithering circuit is basically again driven by this output of the sigma delta only, right? So that's what it is. Then once you have a divided output from the multimodulus divider, you go into PFD, right? And PFD issues up pulses and down pulses, and then there is one more for transient cancellation, that is CCB, right? So we'll discuss that, what that is. So basically a PFD is over here, which drives a charge pump. Now this is a current steering charge pump, right? Which up pulse will pull this node up and a down pulse will pull this node down, right? And it's a tri-state operation of the PFD. So basically, the rising edge of one of them, which is up, for example, and the falling edge, the other of them, will decide the pulse width, right? So if it is if FREF is leading and FDIF is lagging, right? So then up pulse will start with the FREF rising edge, and then drop with the down falling edge. The div falling edge. So basically the divide frequency comes here as Q2 Q2B, and the ref frequency is 70 megahertz, which comes from here. So 70 megahertz is driving as a ref frequency, and 70 megahertz is driving the sigma delta modulator. Now I'm just modeling the locking characteristics. I'm not modeling the phase noise. So right now I have ideal sources here, but in more elaborate simulation, I would put a phase noise on these sources. And how would I do it? I'll explain in other videos, right? So this is a PLL which operates at 100 gigahertz, 98 to 105. So let's go to the first block. The first block is oscillator, and if you look at its, I'm just going to show you the results. I'm not even going to show you simulations. So if I go to VCO and I go to test VCO, right? So VCO core 2, Okay, so this is the one. Okay, it takes some time to open. Okay, so what I'm showing here is the range. Okay, so M6 to M7. So that's a range of 8.2125 gigahertz, and KVCO is 9.125 gigahertz, and the tuning range basically is 1.12 0.2 to 1.1 volts. So that's the tuning range here. So that's the KVCO, tuning range divided by the voltage input to the VCO. That's a KVCO. Now here I am showing you phase noise, and at an offset of 10 kilohertz, I'm having a phase noise of M1, which is 70 minus 70 dBc per hertz. At 500 kilohertz, it is minus 90. At 1 megahertz, it is minus 99. So basically, anything on the left would be the crystal reference, right? So I'm going to hit 100 dBc per hertz in the loop bandwidth. And after that, at 10 megahertz is minus 124. And this I have presented in the previous post, right? So this is the VCO, which has a tuning range. Let's just see it again. Tuning range from 98 or 99 to 107 gigahertz. So that's the tuning range for the VCO. Now, the output of the VCO goes into this divider. So I'm not basically simulating the divider, but this is a master slave. So basically this is the master and that's the slave, and you only need feedback for one of the states. So basically this is just a master slave flip-flop, which is dividing it by 2. So again, I repeat this. So here it is dividing by 4, right? Next is over here, multimodulus divider. So there are 8 of these 2x3 cells, and each 2x3 cell is basically a forward loop, a forward path, and a feedback loop for the swallow circuit. So this forward path is nothing but again a master slave only, and the swallow path is again a master slave, and they are in tandem. So basically this is driven by clock, this is driven by clock, this is driven by clock bar, this is driven by clock bar. So in the forward path, there is only one memory element. In the feedback path also, there is only one memory element. This has been done to speed up this 2x3 cell up to like 50 gigahertz, right? So this is again, these are your single-ended gates. So this is an AND gate, and this is a transmission cell, right? These are your NOT gates, right? So I have done a Fourier differential version also, but then this is just a single-ended version. But the input output are differential here, right? So there is a differential version of this which is slightly better in noise performance, which I'm not showing right now. So this is a 2x3 cell, and that makes a 8-bit MMFD. So if I was to go here and look at the test of this, so if I go to PLL blocks, let's look at multimodulus divider. Okay, so I am dividing, let's see, let me just split this up. Okay, so basically this is one cycle of division, and that would be that would have, how many cycles it will have? It will have basically 372, right? So basically that's the entire divide ratio, right? Now here, the way to do it is I just compute the time period by putting 2 markers, and then you can look at the frequency plot also to see, whether it is that ratio. Anyways, so this is a multimodulus divider which is doing the divide. Okay, now once you have done the divide, you go into PFD, and this is PFD. So I'm just zooming in. Okay, so I have simulated this with the up pulse. So basically ref, I have advanced ref, and I have div coming later. So I have issuing up pulses here, right? So, or I'm issuing down pulses. Let me see. So it depends on how much you advance the ref or div. So you have to see the test bench for this. Okay, so let's see the test bench for the PFD. Okay, so currently delay of 1 nanoseconds, delay of 8.713. So this is 70 megahertz, right? So basically the ref is behind diff. So diff is advanced by 1 nanosecond. So basically this duration of the down pulse is 1 nanosecond. This down is 1 nanosecond because the div is coming faster than the ref. And the up is basically going to be up, and CC bar is going to be over here, which are going to coincide. Okay, so I will explain you what is this up and CC bar is doing. Okay, this is the current steering charge pump, right? So there are three inputs here: up, C, and down, right? They are differential, right? So they go into this charge pump. In this charge pump, it's current steering. So there is a high impedance PMOS mirror and high impedance NMOS mirror. And this transmission gate is basically driven by up, and this transmission gate is driven by down. And this is basically gating the output. So this CC bar is gating that. So when up and down are coinciding, let's see here. So up and down are coinciding here. Then C basically disconnects this from the loop filter, and this basically removes all the switching transients, right, during that period. And the current has to be balanced between a PMOS and a NMOS current meter, and then they have to be high impedance. The alternate path is basically grounded or to the supply. So basically I am operating these in tandem, right? So this node can be pulled up or pulled down again. So this is how the charge pump is working. Okay, the output of the charge pump goes to the loop filter, and the loop filter generates the control voltage which drives the VCO. So this completes the loop, right? So another thing is I wanted to show you charge pump, for example, right? So test charge pump. So basically, this is I'm issuing in one case up pulses, which are going to drive the charge pump from, let's say, 0.5 to almost to 1, and then 0.5 to almost 0.1 here down. So this is up pulses issued, this is down pulses. So this is how the charge pump is behaving, right? For two conditions, lead and lag of the ref and div, right? So this is the simulation for the charge pump. Okay, so I have covered that. Another thing you have to look at is inside the charge pump, these current mirrors, they are to be wide swing. So basically, if you go in here, this is a wide swing cascode, right? Similarly over here, this is a wide swing cascode, right? And if you look at its simulation and its output impedance, right? So let's see if I'm recording. Yeah, so if you look at the simulation of these, right, so you go to test wide swing cascade current mirror. So what I'm plotting here is the current mirror response. So basically 0.1 is where it has to be in this the output transistors have to be in the saturation region. So that's basically a twice of overdrive drop here across the devices. And then this is the blue one is the output resistance I've plotted, and that output resistance is of the order of 100 kilohertz on the way up to like almost 1 megahertz. So for the settling, your PLL basically has to have the least voltage, right, of 0.1 roughly, right? Beyond that, then there is no high impedance. So basically it becomes leaky, right? So it has to be beyond 0.1 output. So which is in our tuning range as 0.1, right? So that's the NMOS. And if I go to PMOS and look at the PMOS, again, so it's operating from 1.2 volts, so I'm losing 0.2 volts, after which there is a high impedance, right? So it's of the order of again 100 kilohertz to 600 kilohertz. So you have to be in the high impedance region. So I'm covering the entire range of VCO by providing a proper high impedance current sources and sinks, right? So this is how the charge pump is designed. Okay, so you put it together and you can simulate the locking. Mesh, I wanted to show you how mesh is operating. So if I go to test, so if I'll go inside what is a mesh. So in my previous sessions, I have covered what is a mesh. So this is a mesh 111. So basically this is a first order integration, this is second order integration, this is third order integration. And then there is a differentiation on each stage, right? So that differentiation is done by the differentiator here, which basically has a differencing circuit here, and then you know this is the first order. Then there is another differencing circuit for the second order, right? So it gives a 3-bit output then, and that basically is your random 0 to 7 states which are fed in here, right? So let me show you that maths also. Okay, for example, let's go to standard. For example, let's say the divide ratio was 375.218, right? Let's say there was a fraction here. So in that case, what would I be feeding? So first of all, I will subtract 3 from it, because 3 is the base for the mesh. The ratio is between 3 and 4. So I'm left with 372, right? So minus 256. That's the base for the multimodulus, right? So I have to feed 116 as a coarse feed. So 116 will go as a coarse feed, which is over here. Now the fraction part left is this 0.218, right? Now the fine feed in this case would be the let's see, where is the calculator? The fine feed in this case will be multiplied by 65536. The total number of states of a mesh, because it's a 2 raised to 6, it's a 16-bit input here, right? So the fine feed will be roughly 14,286, right? Is that correct? Yeah, 14,286. Okay, so 14,286 programming calculator, 14,286. So this will be your 16-bit binary feed into this mesh 111, right? So that will do that. So anyways, so I have explained you how this thing works, and I am showing you the settling characteristics of this guy. So basically, to get the exact fraction, okay, you will have to have the the mesh go through 216 cycle, 2 raised to 16 cycles. That is 65536. That will give you the exact ratio. And also that will give you the noise shaping. Okay, so that means that you should simulate multiple cycles of this, which is each one is going to be roughly 1.3 milliseconds. So if you do a multiple cycles of this mesh, then you will be able to plot the shaping of the noise. So I don't have resources to do that. I have to run this simulation for days. Okay, so I am simulating this only for 1 day, 10 microsecond here. So this is showing that this is going to settle somewhere here, and which is the output of 105 roughly, right? And the divided frequency is going to be 70 megahertz, as that is the crystal. Okay, so basically this sums up fractional N PLL, right, with this characteristics. So well, thanks a lot. This basically was based on all the 30 lectures previously done. So if you want to design this PLL, you should go through those lectures. Another one which I have done, which I'm going to present in the next session, is a 40 gigahertz PLL using 130 nanometer. Right, so this is using 7 nanometer. It doesn't have a complicated divider, right? But when you use 130 nanometers and try to achieve 40 gigahertz, then you have injection lock dividers. So in the next session, I'm going to present those injection lock dividers and the entire loop, right? The same fashion. And then maybe if I have computing resources, I will show you the phase noise of the PLL. But right now, I'm not geared up for that. Okay, so I am going to stop here. And thanks a lot for listening to me. Thank you.